second law of thermodynamics states that no apparatus can operate in such a way that its only effect is convert heat absorbed by a system completely into work done by the system, and no process is possible which consists solely in the transfer of heat from one temperature level to a higher one. This looks like a contradiction because delta U equals 0 for an ideal gas. However, this equation is only in the surroundings and there is no change in the system due to the change in pressure. Since the pressure of the gas ultimately reaches the surroundings and expansion ceases, the continuous production of work from heat would be impossible. Cyclic requires that the system be restored periodically to its original state. The restriction to a cyclic process in Statement 1a amounts to the same limitation as that introduced by the words only effect in Statement 1. This means the devices or machines that produce work from heat in a cyclic process. Essentially, all heat engine cycles absorb heat into the system at a high temperature, reject heat to the surroundings at a low temperature, and produce work. A heat engine operating in a completely reversible manner is very special. It is called the Carnot engine.
The Carnot cycle is fully reversible. Hence, the Carnot cycle reaches the upper limit of efficiency for any cycle, as stated in Carnot's theorem. The Carnot cycle follows 4 fully reversible steps. The first step is isothermal expansion, where the system increases in volume and decreases in pressure while absorbing heat from and being at the temperature of the hot reservoir. During this expansion, the system gives off work. The second step is adiabatic expansion, where the system temperature decreases to that of the cold reservoir while still decreasing in pressure and volume, giving off more work. The third step is isothermal compression, where heat is rejected to the cold reservoir and the system stays at the cold reservoir's temperature. The fourth and final step is adiabatic compression, where the system is compressed until it once again reaches the temperature of the hot reservoir, and the cycle can start again. Backtracking a little bit, efficiency is defined as the ratio of the work obtained from a system to the heat added to the system. Conveniently, the efficiency of the Carnot cycle is only dependent on the temperatures of the hot and cold reservoirs, due to the heat absorption and rejection steps being isothermal. Unfortunately, a Carnot engine is purely theoretical, and no real-life examples exist. However, some engines can still reach relatively high efficiencies, such as the Stirling engine, which in the ideal case operates on a similar cycle. It absorbs heat from an external source rather than an internal one, which allows the use of many kinds of heat sources.
Now we're starting here with the equation for the Carnot engine, which is the QH over QC equals TH over TC. And we can rearrange this by multiplying, change it to QH over TH equals the QC over TC. And since the QC is actually leaving the system, we're going to assign that a negative value. And then we can further rearrange it to show that QH over TH plus QC over temperature cold equals 0. Now here we have a P versus V diagram of a complete Carnot cycle. Now these are all taking place at specific temperatures, and you can draw isothermal temperature lines going through all of this. And each section on the Carnot cycle has its own isothermal region, and as these become smaller and smaller, you can actually break it up into infinitesimally small pieces or differentials for this equation, to where you can make a differential of Q hot over temperature hot plus the differential of Q cold over temperature cold. It will add up to 0 to 2. Through a complete cycle of the Carnot cycle, the values of Q over T eventually return back to their original state, and therefore the sum of all of the dq over t will be 0. And since the complete cycle is reversible, which we can show here, and the sum of all the values returns to 0, the integral over a closed cycle will always equal 0. Since the values of dq over t can be summed up to 0 over any arbitrary cycle that is reversible, we can assume that there is some property that is defined by this dq over t, and the name of that property is entropy. Its differential changes are defined as the change of heat divided by the temperature that the heat source is at, so just dq over t. Now this definition of entropy actually defines the total entropy of a system, which is joules per Kelvin in the metric system, or SI units. Another way to represent entropy would be molar entropy, which is joules per mole Kelvin. You can also rearrange this equation if you would like to make it dq equals t ds. Now the change of entropy of a system for a mechanically reversible process is just the entropy at B minus the entropy at point A. Therefore, you could take any path you wanted to get from A to B, and all three would have the same change in entropy. Anytime the system has an entropy change driven by the exchange of heat to or from a heat reservoir, the change in entropy can always be calculated using the integral of dq over t. If we go back to heat engines, which we talked about earlier, the change of entropy of a heat engine is actually the change of entropy at the hot source plus the change of entropy at the cold source. Now, since TH is always going to be greater than TC, this is always going to be a positive value for this over here. And since Q is always in absolute values, we know that the change of entropy is always going to be positive for a mechanically irreversible process. Now, to sum all this up, entropy is a thermodynamic property which is defined as the change of Q over T. And by integrating this, you can find that the change of entropy is just the integral of dq over T. And for any mechanically reversible process, the change of entropy is just the entropy at one point minus the entropy at the starting point, no matter what path you take. And then for any real-life heat engines, delta S is equal to the absolute value of Q times TH minus TC over TH times TC.